Hello? Okay, hello everyone. Welcome to lecture 3 of our course. Let me start with a few administrative announcements. First of all, exercise 1 is due today. The policy for our exercise is that you're allowed to submit late, but every day that you submit late, you get 10% deduction in the points. 10% or 10 points, I forget. One of the two is listed on the website. I'm announcing exercise 2 today. From now on, first of all, congrats on making it this far in the course. If you're here now, that's good. You kind of survived my scary 2 lectures. I don't think they're that scary. They're not that difficult, but at least you understand the expectations. And you will discover it's not going to be a very difficult if you follow what I'm saying and are doing the exercises and pay attention and willing to invest a little bit at home. You're going to get a lot from the course, I hope. So I'm announcing exercise 2 today. You'll get 2 weeks for that. That will be the standard from now on. So 2 weeks per exercise. The first one was 1 week because I wanted you all to know how the course will look like before you make a decision. And it will be due 2 weeks from today on the Canvas/GradeScope. Do we have it prepared, Rohit? I think we do, right? We have. Okay, so Rohit is gonna, or the TAs are gonna put it on the Canvas website. This Thursday, final announcement, this Thursday I'll be away. I hope this is the only class I will miss. But nevertheless, class will take place. So Rohit Agarwal, my student and TA for your course, will be lecturing in my place. It's going to be a regular lecture. All the material is integral part of the course as usual. And he will talk more about optimization. So now I will start today's lesson. Today I'm going to talk a kind of end-view. It's going to be I hope, a very interesting talk. This is a talk about online convex optimization. Much of what I'll talk about today is covered in chapter 3 in the book Introduction to Online Convex Optimization, which is available off archive. But I would actually encourage you to come unprepared. That is my encouragement to you. Come unprepared, listen to what I have to say, and then follow up with reading at home. It will be nicer to you, and also when I ask you questions, I will get real answers rather than something you already studied. So I motivated last week. We started talking about prediction from expert advice. And what I'll talk about today directly leads to the setting that I'm going to describe. We ended with discussion of online shortest path problem, which is a very interesting mix of graph theory, decision making, and computational issues that arise because there could be a lot of paths in a graph. Exponential in its natural description. Right? So this led us to think about, is there some kind of model that allows us to make decisions in a similar way to we did with prediction from expert advice? Efficient algorithm, simple analysis, guarantees that do not depend on statistics or on probability. We would like all these features to happen, but we'd also like an efficient algorithm. You guys remember what we discussed on Thursday, right? You all? Good. So that led us to talk a little bit about convex relaxation or convex language to describe decision sets that are more complicated, like paths in a graph. And we saw how using the language of convex optimization or convex analysis, we can talk about the convex hull of all distributions over paths in a graph from source to destination, and that happened to be a flow. And we talked about the set of all flows, which is a very nice shape, geometrical shape in Euclidean space, which is called the flow polytope. That is our motivation. I'm now going to talk about a framework that generalizes this further and allows us to talk about decision making in a very general setting. It is called online convex optimization. Since its inception, it has become very popular and still state of the art in modeling a lot of real world problems and has led to a lot of very interesting methods. And in fact, the adaptive gradient methods that are used to train All deep learning today, including LLMs, are based on techniques that I will describe. What is it that made it successful? And I will say the properties here because I think I want to convey to you not only the material, but how to think about theoretical machine learning in general. There are several, I thought about this morning myself. There are several aspects of the definition of the framework that make it very successful. One of them is a good formulation of the goal, which is regret, that we discussed a little bit in its form of prediction from expert advice. We related the loss of our decision maker not to an absolute loss, but to the best expert in hindsight, relative loss bound. This is a very general and a very good metric because it does not rely on statistics or probability or complicated definitions. It's a deterministic quantity. If we have a randomized algorithm, it can be expected regret. Nevertheless, it's a simple quantity to describe. It is always defined, and it is very general. It applies in very general situations. I don't need the specific behavior of the environment to define it. The other, which I think is equally important, if not more, is efficient algorithms. So we talked about the multiplicative weights method, weighted majority and randomized weighted majority, and then hedge algorithms. These are very simple and very efficient algorithms that you can code up very easily. I wrote the pseudocode, 2-3 lines of code here. And that always is a good, appealing thing to have. Next, and I think that's also very important, is simple analysis. When you can write down your algorithm, very simply describe it, and analyze it in a way that I can, in one class to you all, which is probably half undergrad, half grad population, from start to finish, I analyze an entire theorem and prove it. That is a very good property, because then you all can take it home, the next generation of researchers, and think about it and develop it and enhance it and use it as a building block in whatever you are doing. That's a very useful thing to have. Right? So when you have a simple analysis, that's a very important property. And finally, the third property, these all were present in prediction from expert advice. The one extra component which I'm adding today is convex relaxation. And that is a more elusive component. It is not a very general property, but it's a property that applies to the setting that I will describe and makes it very useful. It will allow me, for example, to take the problem of online shortest path and represent it in this framework. And it is able to allow me to represent many other decision-making scenarios that maybe on the face of it don't look to be so simply describable, and yet they might have a combinatorial structure or complicated structure on the face of it, and yet the language of optimization allows us to convert it to a mathematical program which is easily solvable. For many years, this was applied successfully to combinatorial optimization problems, and more recently, even to control and reinforcement learning. So this is a very strong property that we will use later on in the course extensively. Let me now define the framework, and then I will give an algorithm on how to, an algorithm, an analysis that applies in this generality. So the setting, I will need a few concepts from convex analysis that I think you're all familiar with. If you're not, I will give a very brief definition saying what they are. I think you already all know what the convex function is, a convex set, right? Am I right that you all know what it is? Very good. So I think all of you know that. I will just give a very brief reminder. And on Thursday, Rohit will talk a little bit more about convex optimization in generality, not online convex, just offline convex optimization. I also think many of you know that, and give a slightly more rigorous treatment. So here I will only give you what I need for this class. And I need very little. So one is I need the definition of a convex set. A convex set, call it K, subset of R to the D. I'm going to use D for dimension, and Euclidean space R to the D. It is convex if for every x and y in K, and for every alpha, which is a real number, between 0 and 1, the point alpha x plus, so alpha x plus 1 minus alpha x, y, also belongs to K. So this is an if and only if. A set is convex if it satisfies it, and if it doesn't satisfy it, it's not convex. So you want it to be nice and round. For example, this is a convex set, but this is not a convex set because you have these 2 points here, and their midpoint is not inside. You've all seen this, right? Good. And if not, that's all you need. Number 2, I need a convex function. So that I believe even in high school and even in the America, it is being taught. So we have a convex function means that it looks like a smiley. So when you take a point and you take the tangent line to the function at the point, the entire function lies to the above it. This is called the convex function. Or if you want, I can say that f of y at any point y, I have here is x and here is y, it's bigger than f of x plus the gradient of f at x times y minus x. So this is a mathematical definition of a convex function. There are many equivalent definitions using the convex underset and so on, which I'm not going to go into. Maybe Rohit, if he needs it, he will do it Thursday. And if not, you all remember that. I think in high school you also learned that the second derivative, if double prime, is non-negative. So if the function is twice differentiable, and if it's one-dimensional, then the second derivative is non-negative. If it's a high-dimensional function, then the Hessian of the function. So in high dimensions, we have the second derivative is a matrix. Have you all seen, this is a multivariable calculus, right? So everyone here okay with this? Yeah? So the Hessian is positive semi-definite. You're also fine with this notation? Yeah, so this means that all the eigenvalues are non-negative. Okay. And the Hessian is defined to be Hessian of f at x ij is the derivative with respect to xi times the derivative with respect to xj. So it's a symmetric matrix because you can replace the order of differentiation. And it is not necessarily positive semi-definite, but if the function is convex, then it is. That's the generalization of non-negative in one dimension. So this is, I think it's high school material because my son is a junior, even though he's good in math, and I think he studied all that in his high school. So one more thing I need, last property I need, and that is probably not, actually it is in some form studied in high school also. This is called the Pythagorean theorem. But a slightly more generalized version than maybe you saw. So when we have a convex set, and we have one point inside of it, which I'm going to call x star, and one point outside of it, which I'm going to call y, the projection of y onto the convex set, or any set, is just the closest point to it. It is unique. If the set is convex, this is a unique point. So this I will call pi of y. Pi for projection. Then the following holds. So the distance between y and the pi of y is smaller than the distance between pi and x star. Okay. Or in other words, the distance between pi of y and x is smaller between the distance between y and x star. That is true because this angle here is obtuse. That's the relationship to the Pythagorean theorem. So if you put a tangent through the point of intersection here, this is the closest point to y, this is 90 degrees, it's going to be an obtuse angle, and that is why we have the triangle properties here, that this is smaller than this. So let me write it formally. If pi of y is equal to the minimum x in k, distance x to y, that is the definition of a projection. Then Pythagoras said that the distance between pi of y and x star is only smaller than the distance between y and x star. Am I saying the name correctly in Greek, Raphael? Pythagoras? Yeah? Good. Okay. So far, everyone have seen this? You're all comfortable with what I said? Euclidean geometry? And a very, very small amount of convex analysis allows us to do the following. Let me give you the first algorithm for online convex optimization, which is called online gradient descent. OGD for short. Oh, wait. Before I go there, I need to define the setting of online convex optimization, which I forgot to do. So OCO, online convex optimization. So a decision maker plays xt from a convex set K. Then an adversary gives convex cost function ft from K to the real numbers. Then the decision maker pays or loses ft of xt. And then this is repeated again and again and again. So that is the setting. Similar to our discussion of prediction from expert advice, we're making iterative decisions. We're choosing, these decisions are now not A or B, and not even choice of one amongst n, like prediction from expert advice, we had a discrete set of decisions to choose from, correct? Now we're choosing a point in a set, which is you can imagine a much more general situation, right? And how is our loss determined? Again, it's not n numbers, like prediction from expert advice. It's much more general. We have a convex set that gives a loss to the point that we chose, and so on. Just to see that we're on the same page, let me ask you a question. So, can I model prediction from expert advice as a special case of online convex optimization? Yes, why? Your name again? Mine, yeah. Uh-huh. Correct, but notice that choosing an expert from n possible experts, it's not naively a convex set. Right? You have a discrete set of n experts. So how can I model? Yeah, Ben? Okay. Okay, good. Okay, very good. So Ben is saying the following. I can model prediction from expert advice as a special case in the following way. By the way, if you read the book, that's cheating, okay? Don't answer me if you read the book. And then the set, you can look at the set of all distributions. So all distributions, they form a convex set. All distributions meaning all x in simplex D such that summation xi equals 1 and xi 0. So this is a subset of R to the D. It's called the simplex. It's all distribution over D elements. D is n. N is the number of experts. This is a convex set, and you can choose a point from it that will correspond to a distribution over the experts. Now, what would the loss look like? So if you already read, Ben, you want to continue? No? Someone else? Yeah, Colin? You started correctly, but okay, sum of what? Yeah. Okay, fine, of what? Yeah, you're right. Colin, continue. Convex of what? Combination of what? Uh-huh. Yes. Exactly right. So what Colin is saying is the following. Let's say that there was a loss LT of I. This was the loss at time t to expert I. What is my expected loss at time t if I choose a distribution xt? Yeah? Correct. So in vector notation that I used last lecture, it was xt transpose LT. That is summation over I, xti, LTI, right? So this is the expected loss. If I choose a distribution xt, that is my expected loss. What kind of function is it in the variable x? Is it a convex function? Of course, it's a linear function, right? It's a linear function in RD. So I can model prediction from expert advice as a special case of online convex optimization. Well, for that, I didn't need to define convexity and all these complicated things that I defined. I must gain something more, and what I gain more is, for example, the ability to model online shortest path. So how can I model online shortest path? Kind of touched upon it last time. Yeah? What is that convex set? Yeah? What is that convex set? Yeah. That would work. That's a good point. I could have created a simplex where the dimension is the number of passes in the graph. I could have done that. That would work. That would have been inefficient, right? Because that will be exponential potentially in the number of vertices. Raphael? Oh, very good. So I could have taken K. So for online shortest path, I could have taken K to be the flow polytope from S to T, as we saw last time. That doesn't leave an exponential dimension. It leaves a dimension which is the number of edges in the graph. It has a nice succinct description. You can do flow decomposition and all these nice things. The harder thing here is to say what the losses look like. Do you remember, Raphael? Very good. How about I won't write it down for now, but I'm happy to do it later. So to write it down, I will need to write what a flow is. A flow is you have a weight for each edge, right? Just 1 second, Colin. So we have a weight for each edge, and then we sum up the weights of the particular edge times the flow over that edge, and that will correspond to the probability that I pick that edge in the weighted combination of passes that I have, which is my flow. Yeah? Question, Colin? Over T? Yeah. Ah. Yeah. Yeah. That's a good question. Let me see if I'm, and I know why Colin is asking that, because he's thinking of further up the course where we'll be talking about time dependence between different decisions. And that is extremely important in today's world when we do LLM and next token prediction and control and world models and so on. We will need more assumptions for that to hold, and we'll talk about extensions to that situation. But what I'm describing today is more general and simpler. And magically, you can still do something in this setting. So I think, I know why you're asking that, but, and even, let me ask you, all of you, the audience, what can be my goal in online convex optimization? What would be a good metric of performance that I should try to optimize? What can I hope to achieve? So look, it's a very general setting, right? I'm picking a point, and then I get a number loss, and then I pick another point, I get another number loss, and so on. So what can I hope to do in this situation? Yes, over there? Okay, good. So that is the analog of what we did for prediction from expert advice, right? You all agree? Good. So the goal in online convex optimization is to minimize regret, which is defined to be the sum of the losses that I pay minus the best point, which I denote by x star and k, loss in hindsight. So this regret is defined as a difference between two quantities. One of them is what I paid, and the other is what I would have paid had I seen all the costs ahead of time. This is not defined ahead of time. It's not defined. The reason it's not defined because the sequence of losses is not defined yet. That's something that happens online. So this is defined only a posteriori. Only after I have seen the entire sequence, only then I can say what I competed against. Okay. Question?
I have a nitty-gritty question. Why
Yes.
are we taking as our baseline a fixed action, fixed element in the convex set instead of general vectors?
Yeah.
Depend on t.
Yeah, very good question. So let me repeat it because I have a YouTube audience. So the question is, why am I comparing to the best fixed point, x star, and not something that's changing, something even a bit more powerful? There's several answers. You know what? Let me try to give the audience a chance to answer that. Who can answer? Someone who didn't participate yet. Yeah, you? That is correct. It could be. It could be. But then what's wrong with that? Well, analysis will be harder because you can't do it. That's why it will be harder. So it's just impossible. It's impossible to compete with the best changing comparator. Think of the following situation. For every iteration, with even prediction from expert advice, you can have two options to predict, or n experts to choose from. You choose one of them, and whatever you're right, you're wrong, it doesn't really matter, but the best for that particular iteration could have a loss of 0. So you could make sure that this is always 0 if it's non-negative, for example, or minimally low, and then this is meaningless. This is going to be meaningless. You're only trying to maximize your own loss, and that already we discussed is basically hopeless if you don't have an underlying model for generating the costs. So it's too hard. Think of just one iteration. What can you do in one iteration? Nothing. You can make some decision. You don't know what's going to happen, and then something happens, and great. And the same thing is just happening if you don't have any restriction on the x star. Let's say it can change arbitrarily. It's basically the one-shot scenario happening every single time. There is no difference between the different iterations. There is nothing that will connect them one to another. Oh, I like what I said right now. I never said it before, but I think this is a good explanation. Does it make sense what I'm saying now? Yeah, there is nothing to connect the different iterations. I'm having a one-shot trial with no model and nothing to help me every single iteration. So this is clearly not something I can win at or get any meaningful guarantee for. However, you could, I think what you're asking is something a bit more refined. Maybe I can compete with something more in between. So changing slowly or every once in a while it changes and so on. There are metrics that do that. Maybe we'll talk about them in the course. Sometimes they're interesting, especially in dynamic environments and changing environments. Then you do want maybe there's a shift in the environment. You want to all of a sudden, wait, this X star is stale. I want to compete with something else. And then it becomes interesting. But nevertheless, it is still the case that just vanilla regret is the accepted and best thing to look at for almost any problem you can think of initially. Then you can make all sorts of refinements and improvements and so on. But this is still the case. This is a very general metric and gives rise to very non-trivial guarantees. Yeah?
Sorry, can we just learn some dynamic of function structure? I'm thinking about the example in which
Yeah.
the adversary always chooses the opposite, like
Yeah.
chooses
Yeah.
alternating A.
Right.
You cannot hope to learn that.
No, this is a really good question, very important question that you're asking. What's your name? Eduard. Eduard's question is, can we learn anything about the sequence of loss functions? And the way I've defined it, again, think of the general, simple setting. I'm not assuming anything about it. So there is nothing to learn in some sense. It can be maximally adversarial. It can be the same function every single time, forever. That's a very easy situation. I don't want to make any assumption here. And it's a good philosophical question. Why don't I want to make any assumption? Maybe I do want to make an assumption. Well, you can make refinements later on if you have some more knowledge about the problem you're learning. But it turns out that the generality here is very useful. And we're going to apply this framework not only to, well, you already saw that it generalized prediction from expert advice, which by itself is a wonderful thing, and shortest path and complicated problems, but to decision-making processes beyond online learning, like control and reinforcement learning and so on. So it's a very general, this generality allows much more applicability and rather than restricting ourselves. But you can definitely, people have, and we're going to apply to playing games, playing zero-sum games and solving linear programs and all sorts of things that you maybe don't see immediately. But this kind of generality allows us to do so. Okay. More questions? Yeah? Good question. What happens for a randomized algorithm? I will usually look at expected regret. So the expectation is over the randomness of the algorithm. And the way the rules of the game are, you remember from, I believe, Thursday, we talked about prediction from expert advice or randomized weighted majority on Tuesday. The rules of the game are the same. When the decision maker plays, she is able to randomize amongst a different set of decisions. The adversary is not allowed to see the outcome of her random choices. He can see her distribution, that's fine, but not the outcome. And then there is a loss and so on. So that is the extension. I'm not going to write it down very formally, but I hope that's enough. More questions? So let me talk about online gradient descent. That's the first algorithm we're going to see for this setting. It's a very general algorithm. It's a very easy algorithm in terms of describing it, simple analysis, simple description, very efficient. And it applies to this very, very general setting. So here's the algorithm. Initially you play some x0 in k that can be initialized arbitrarily. And then for t equals 1, 2, and so on, you play xt, you see ft, you pay ft of xt. So far, I didn't say what the algorithm is. This is just a setting. And here's the important part. You update xt plus 1 is the projection of xt minus eta gradient ft at xt. Projection onto k. So let me describe geometrically what's happening here. This is our convex set K. And here is xt. Xt is the current point that we're playing. We played it without knowledge of what's going to happen. Then we see a cost function, which is convex. And that cost function has a gradient, so maybe the gradient is pointing to this direction. We take a step. Eta is some parameter. We take a step according to negative eta gradient. That might lead us here. And then we find the closest point, which is the projection of it. So this is xt negative eta gradient ft xt. And this is the projection. So why do I need a projection? Because I might have stepped out. Right? The gradient might have been very large. I might have taken a step outside the set. I need to make sure that I'm playing inside the set. These are the rules of the game. You cannot play outside. That's not allowed. I should be able to have access to the gradient of the loss function. That is required, which is some restriction, not a huge restriction. We'll see how to remove it at some point. It's a very minimal requirement. We need to be able to project back onto the set. So there was a question here about randomized algorithms. It's a good homework exercise to think that in what I've described so far, you might as well restrict yourself to deterministic algorithms. They're always better in some sense. It's an artifact of convexity, something called Jensen inequality. You can think for yourself. It just occurred to me that I had to tell you that. So deterministic algorithms are fine for now. It is that the function of the expectation is always smaller than the expectation of the function. That's part of convexity, and that's why you should always, if you have some distribution, just play the expected point. It's going to be better for you. There's no point to do something else. Yeah. Yes. Okay, that's a good question. What information do we need? What do we need to implement this algorithm? What do we need to implement? So we need the following. We need one to take gradient at xt. So we need that. And we need to be able to project onto K. So amongst these two that's it, right? Everything else is pretty elementary. I need to add the two numbers and, right, that's it. So taking the gradient is relatively a pretty lenient requirement. For most loss functions that we will encounter, that you can think of, it's not a problematic situation. Are you thinking of something where there is an issue with that? Yeah. Well, for a scalar in 1D, it's a number. It's a derivative is a number. But in higher dimension, you will need a vector. You need a direction. So it's not just a number. It is enough. It is enough to implement this. Yeah. You don't even need to know what your loss is, in some sense. It doesn't matter for the algorithm. But if you have, in one direction it's x squared, in the other direction it's x cubed, and so, some other funny thing, then you will need the gradient. You'll need every single coordinate to know what the value is in that, for that particular point you're at. Yeah? That's a very good question. Let me just get back to it in a minute because I didn't completely answer your question. So number two here, let me just get back number two here. Projection. That's the second thing I need. Projection is a much more, I would say, difficult requirement. You can have sets that appear to be difficult. For example, the flow polytope. Projecting on the flow polytope maybe is a non-trivial problem. It is the case that for every convex set, projecting onto it, meaning finding the closest point from point outside to the set, is a convex optimization problem, which means you can solve it efficiently. I'm not going to go into it now, maybe later in the course. For now, you have to believe me, it can be done efficiently. There is an asterisk here. So how is the convex set even described? How do I describe a convex set? Obviously, I'm not going to have a database of all the possible points that belong to it. That's not an efficient representation. If it's a polytope, I can describe it by all the half spaces. That's an efficient representation. That's fine, if there are not too many of these. Otherwise, I could have something called a membership oracle or separation oracle, various constructions that describe the convex set. I prefer to keep it clean for now and not go into these details, and we can go into them later. Or if you ask me even later in the class, that's fine. I'm happy to go into the details, but it distracts from the very elegant thing I want to show you now, okay? I want to show you something very beautiful. So let me first show you that, and then you can ask me the nitty-gritty stuff. Ben's question was very important. He asked, how is it possible that I'm able to do something at all if these FTs are changing every single iteration? And the answer is that I'm going to prove it to you that it is possible. I mean, it is a surprising thing. I'm happy that you find it surprising. That is true. If you don't find it surprising, I failed at something. You should find it surprising that it's possible to do. Let me give you the theorem, okay? And then you will see it's a beautiful theorem. So theorem. For eta, which I will soon pick, so it's going to be something like so 1 over root t. There is some more constants here that I will fill in a minute. The regret of OGD, which I've defined as summation t ftxt minus minimum x star in k, summation ftx star is less than dg root t. Well, so g is an upper bound on the gradients, so all the gradients of the functions at xt are bounded by g, and d is an upper bound on the diameter of k. Diameter of k is how wide that set is. That is equal to the maximum over all xy in k of x minus y. So how far away can 2 points be inside of k? That goes inside my bound. If I can go to infinity, you can imagine maybe this x star is also to infinity. There is no way I can reach it. So it's clearly, I need some kind of bound there. The other is I need these functions to be bounded, because if they're not bounded, maybe I assign a loss of infinity to myself and 0 to some other point. You can see that there could be an issue if there is no bound. So I believe it's something like d over g root t. Yeah? Yes? This term? It's fixed a posteriori. It's not fixed a priori, right? So it depends. This x star depends on which ft's were chosen. That's right. Yeah, that's true. This is an important question. So why do I need this x star at all? Remember when we talked about prediction from expert advice? It could be the case that all experts are horrible, in which case I cannot guarantee anything by myself to the losses that I obtain. I cannot guarantee anything about it. I can only guarantee something compared to the best in hindsight. So if they were all horrible, I did horrible, but they also did horrible. Oh, I did great, actually. From my perspective, I did great. Does this make sense? So if there is one person here, he made $1 million, I lost money, I'm going to feel terrible. But if all of you lost money and I lost money too, okay, we all lost money. We're all kind of the same aggregate. There's no one I could have listened to improve my situation. Right? Very important question, very important concept. That's crucial to the definition of regret, and the reason I'm able to do something at all. If I don't have this term, I'm not able to say anything. There's no way you can say something in this generality that I'm talking about. Yeah. If what? Yeah. Not of this type. Not of this type. There is something, you can still define regret with respect to a certain class of X stars, not with respect to the set. And then you can say something. You can say something very similar to what I'm saying. In fact, it's probably one of our exercises. So, but if you don't a priori, if you don't have no bound at all and you don't want to restrict the X star, I can just give you a situation where you have a linear function, sequence of linear functions. So here is a setting. Plus x, minus x, plus x, minus x. You don't know if there are going to be more plus x's or minus x's, and the solution is going to be either at plus infinity or minus infinity, and there is no way you can compete with that, right? So what I told you now can be made into a formal lower bound. But if I bound somehow the set of comparators, that's fine. So either the set, but it's kind of the same, right? Bounding the set of comparators and bounding dk is the same thing, pretty much. Yeah. Yeah? Yeah, absolutely. Very good, Colin. Because I think what Colin is getting into, otherwise I could have quadratic function that goes to infinity, right? So there is no way I can say anything meaningful. But these are very, does anyone have a problem with these definitions? I mean, these are very lenient kind of restrictions I'm putting here. Boundedness, pretty much, and that's it, almost. So convexity is the serious restriction here, but boundedness is not really a serious restriction, in my opinion. Very good. So this is the theorem I want to prove. Before I prove it, any questions about it? Do you see that it's I think it's a very surprising and a very powerful theorem. It's a very powerful theorem. In a very general setting and a very efficient and simple algorithm, I'm able to achieve this. Okay, let's prove. Question, Colin? Oh, can you do that? Thank you. Thanks for the reminder. Yeah? No, convexity is enough, actually. It's a good exercise. You don't need continuity. So for the gradients to be defined, you need continuity. I'm now assuming the functions are one continuous for simplicity. If they're not continuous, I'm okay with suffering countable number of discontinuities, and then you can define something called a subgradient. Subgradient is something that satisfies the convexity property, which I have probably erased. So you need something to upper bound the function from below. Okay, but it can be more general. So that is Lipschitz gradient property? No, it's not needed here. I don't need it for this function, for this. Why would I need it? Well, convexity and boundedness function is enough for here, okay? But it's a good exercise to try to prove it. Yes. Okay. Actually, I take it back. You could have a situation where you have an unbounded. Look, I can define all these weird creatures here, like, Dirichlet functions or whatever. I'm not going to do it. That's not really the interest of me. But you could have a situation, I take it back, you could have a situation of a function going like this, all the way to infinity, and then the gradient here is going to be very large, and this g function is going to be, this g parameter here is going to be maybe unbounded. So I'm assuming it is bounded. So this bound will depend on the g, okay? Yeah? Yeah. It's what? It's continuous. Yeah. But this is a continuous function here. You can make the slope extremely large. I mean, this could be, right, it could be a very small domain on the line, and this could be you can make it as large as you want. So potentially this could be extremely large. Again, assume that I have a bound G on the gradients. If you find me a scenario that is of interest and that's not the case, I will be intrigued. I am not familiar with such. Are you familiar with such a situation? I'm not familiar. With a real situation where we have, these are very, very lenient assumption that I dare you to find me a problem that these are not satisfied. That's an interesting problem and cannot be modeled that way. So yeah, let's prove the theorem. Any questions about the theorem? So let's look at the distance between xt plus 1 and x star. This is the norm here refers to Euclidean norm here and for the rest of the course. So this is the projection of xt minus eta gradient ft at xt minus x star. By definition of the algorithm, and I claim it is at most xt minus eta gradient ftxt minus x star squared. And why is this true? Correct. So this is by the Pythagorean theorem. So Pythagoras. And this is equal to xt minus x squared minus 2 eta gradient t xt minus x star. Here I'm denoting by gradient t, gradient of ft at xt, just for simplicity of notation, plus eta squared norm of gradient t squared. And this is true because a minus b squared is a squared minus 2ab plus b squared. That's why it's true. So let me shift sides and write the following. Ft of xt minus ft of x star. And let me sum up over all t. So this is the regret. That's what I want to prove something about. This is at most summation t, gradient t, xt minus x star. Transpose. Why is that? Yeah, convexity, that's right. It's convexity. Remember, the convexity means that the function lies above the gradient approximation. So this is the one and only place that I use convexity. And this is at most 1 over 2 eta summation t xt minus x star squared minus xt plus 1 minus x star squared plus eta squared gradient t squared. This comes from here. Let's call this star. So this is from star. And this is bounded by, so these all telescope. The quadratic terms here, I have xt minus xt plus 1. So it telescopes when I sum up over t. And I'm left only with 1 over 2 eta times x1 minus x star minus x big T plus 1 minus x star squared plus eta over 2 times T times G squared by the gradient bound. So every gradient is bounded by G, and I sum up T of these terms. So it's at most Tg squared. And this is bounded by 1 over 2 eta d squared plus eta over 2 Tg squared. And now what did I choose my eta to be? Over there. So I was correct. Yay. So this is at most dg root t by choice of eta. Questions? Yeah, Jerry. But one of them is negative, right? So I just got rid of it. Right, so this is not negative. Yeah. Yeah, this is tied up to the constant. You know, the constant is 1, dg root t. Look what a beautiful theorem. So there is no asymptotics here, no approximation. Very efficient algorithm and works even though, so Ben's question is spot on, okay? I'm taking a gradient step in a direction which might have nothing to do with the next loss function that I'm gonna happen. So every time I'm taking gradient step to a loss function that happened already, the next one I'm not restricting it, can be totally different direction, and still I'm getting a convergence of some form. Right? This is an interesting, it's a non-intuitive theorem. Yeah? Well, if the gradients are very large, any method would fail. You have to reasonably, right? Because the gradients are pointing something very, it's going to go very wild. Your optimization procedure is going to go very wild.
I mean more like one.
Well, this is the optimal bound you can obtain. That's one of them. So they cannot do any better. That's one intuition. The algorithm, I think, is very intuitive. The intuition here is not, there is intuition coming from the bound. The intuition is statistic. You will explore that in your homework. So this is the best possible regret you can obtain asymptotically in both D, G, and T. You cannot do any better in all parameters. So if your gradients become larger, your regret has to grow with the gradients. I think this is simple to see. Anyone sees why? Yeah?
If the gradient is higher, it's more steep slope, so it takes more.
Okay, that's true. That's intuition true. But I want to kind of a proof intuition. Proof. Who can prove to me that gradient, if I multiply the gradient, all the G bound by factor 2, my regret has to grow by factor 2. Yeah. That's a good intuition. But there is a mathematical sense in which, look at these functions. Suppose they are linear functions. If I scale them by factor 10, what will happen to the regret? It will scale by factor 10. It's a scale variant quantity, right? There is no way I can get rid of a linear dependence in the gradient norm. Just by the fact that if I scale all the functions by 10, I'm going to have factor 10. And it makes total sense also. So the intuition is correct, but you can see it mathematically very easily here. Okay? Diameter, also you can think of it. If I have double the search space, of course, I can have double the magnitude of costs. And you can see that also very easily. Just think of linear functions over the line and take the domain to be twice as large as it was before. Okay, I might as well play the endpoints, and they're going to be twice as large. So there is nothing you can hope to do better than that. And that's the reality of it. That's just the reality of it. It's scale variant quantity. If you lose one, you lose one. If you lose two, it's twice as bad as if you lose one. It comes from this fact, nothing more. The square root number of iterations is a fantastic result because it means that on average, if you look at the average regret, you scale the regret by factor 1 over t. So let's do that over here. Let's look at the average regret. One over t, summation t, ft x star. I claim this is less than 1 over t, summation t, ft x star. So this is the average payoff, plus something that looks like dg over square root t. So this goes to 0. So on average, I compete with the best point in hindsight. This will correspond, if you map it to prediction from expert advice, it will correspond to competing with the best expert in hindsight. If you map it to only the shortest path, it means you will pay as little as the shortest path in hindsight plus something that vanishes to 0. Okay? ft of, what did I write? This, oh, yeah, sorry. Yeah, Jerry? Well, this is not the finest bound you can obtain. I mean, if the f changes, you're talking about the situation where f changes very, very mildly from one iteration to the next. And yet, in some situations, it is tight even for that. So even if it's the same f, every single iteration is the same f. Suppose what will happen? What will happen to this? Well, I have here summation, one average of the same function applied to xt. So it's the average point I got. So you can think of f of the average. F of the average is only less than average of the f. This is by convexity or Jensen inequality. What does this become? Just f of x star, if it's the same f all the time, plus something that looks like 1 over square root t. So the conclusion here is that the average point, the value of the is the same offline optimization. The average of the point that I take here is at most the best in hindsight plus 1 over root t. So I'm solving, one special case here is solving just general convex optimization at this rate. In full generality, with just a gradient oracle, this is sometimes, there are cases where this is tight, cannot improve it. Even if it's the same function, not changing slowly or anything like that. Same exact function. Yeah. I see it bothers you a lot. I'm very happy that it bothers you a lot. It means that I did it right. This should be a magical result to you. It should be a magical result. Nothing I will say now will resolve it. I'm saying this from experience, okay? I'm myself have struggled with it. What's going on here? How is it possible? It looks like pure magic. Not only that, when I was a grad student, I studied these things from the point of view of portfolio selection. I was interested in that topic. And some of the algorithms I will show you, these are from my thesis. You know, I worked on this and tried to apply it to portfolio selection. And I couldn't understand how can it be. And not only that, I can actually map them to the stock exchange and potentially, you know, run algorithms, trading algorithms, and succeed very incredibly well. That's what the math says. Yeah, I mean, there is no nothing I will tell you here will resolve that. You just need to get used to it. So some things in mathematics, the intuition builds over time. It's not like I can tell you one thing and you will. But I think the best thing I can tell you is the following. It doesn't guarantee that you're going to do great. It doesn't guarantee that. It guarantees that you will do great compared to the best in hindsight, best fixed in hindsight. So that alleviates some of the intuition, I think, some of the issues, because if everyone is doing poorly, you're also doing poorly. It doesn't guarantee anything in that situation. Okay? I hope that will. No. There is nothing to do with finite dimension. This is, if anything, these methods are very well behaved with respect to dimensions. And if you, I didn't even say here that I'm working over a finite dimension. There is nowhere I say that. These methods apply to infinite dimensionality. So I need a bound. They need to be Lipschitz bounded. There is some Lipschitz bound on the gradients, a Lipschitz bound on the domain, and so on. But it doesn't have to be finite dimensional. That's actually one of the strengths of these arguments. And they go beyond many methods that apply only to finite dimensions. So there is no dimension doesn't appear at all. Yeah.
Let's say you reshuffle all the alpha. So like basically like the second regress term would be the same. Or reshuffle.
Yeah, that is correct. Yeah, that is correct.
But the bound still works.
Bound still works. Bound works if you reshuffle, you don't reshuffle, do whatever you want. Same f every time. Actually, one of your homeworks is the following. Suppose f, this captures stochastic gradient descent. Suppose f is a stochastic function. So it has the same expectation, but different instantiation every single iteration. You will get a meaningful result here, similar to what I wrote here, but by taking expectations, you'll get a very meaningful and interesting result. And that actually shows some of the power of not using statistics and probability and all that in the modeling. I can put it on top of it. I can look at the special case and apply my deterministic bound and get some interesting conclusion to stochastic optimization from here. But that's true. The bound is the same if you reshuffle. That is absolutely correct. Yeah. I wonder if I have time. Yeah?
I had a question about what you said about applying portfolio selection.
Yeah.
Because markets have lots of structure in them,
Yeah.
A lot of structure which could be used for, effective risk management. It's easy to see correlations and things like that. Is there a problem with trying to apply this framework to something like portfolio selection where you care a lot about things other than, your expected value? You care about, variance and risk and things like that?
Historically, much of the literature on this topic came from portfolio selection, actually. And there is a long history going to Thorpe in the 50s, and then later on, so he talked about betting in a favorable casino. So when you bet in a favorable casino, there are several. Let me give. This is a very nice vignette that I can tell you about. So I don't have too much time. I'll just tell you a few vignettes. I thought I will manage another proof today. It's not going to happen. I'll tell you some fun things. So think of the following bet. This is due to Thorpe. I believe. And he describes it. And the original called Cayley criterion. Did you hear of Cayley criterion? Anyone here heard of the Cayley criterion? Yeah? Some of you did. There is a rumor that, what's the name of the big hedge fund manager, Berkshire Hathaway? I forget the name of Buffett. That he uses that to manage his bets. So you can think of like a situation where with probability 1/3, you gain 6x. And with probability 2/3, you lose everything. Lose. All. Okay? So this is a favorable bet. Right? So how much do you gain on the expectation? If you put $100, how much are you gonna, what should you do with your $100? I give you $100 and I'm giving you the option to bet on this setting. What are you gonna do? All in, of course, all in. Of course. Because your expected value is $200, right? So here's the question he asked. What if I allow you to repeat the bet 1,000 times? Same bet. You have to tell me how much how many X dollars you have, you're going to reinvest. Now what do you do? Miss Ella Colby, what are you going to do? How much of your money are you going to put in? You can put 10%, 5%. What will maximize your expected wealth? Yeah, over there. You want to get as much money as you can and as quickly as possible. Yeah, Edward? Of course, you need to go all in, right? You need to go all in. If you go all in, you're going to make 2 to the 1,000 times your initial wealth money. That's your expected wealth. However, you're all laughing. Why are you laughing? Because what's the probability this will actually happen? The probability this will happen is 1/3 to the power 1,000. It's not going to happen, right? So what happened here? You don't only care about the expectation, you care about some probability measure, right? And it turns out there is a ratio, this is called the Cayley criterion, there is a ratio that with probability 1, if you invest this ratio, it's going to perform better than any other ratio that you put in. So you would say, okay, I'm going to put 10%, 5%. It turns out the expected logarithm, that's the expected logarithm of wealth, that will, with probability 1, give you much higher wealth than any other percentage. Okay, so that's a very interesting. Did you guys see this before? Hear about it? Yeah, some of you. Oh, Jerry, you know that? Probably finance interest or something. Okay. So this is a very interesting, right? It's a very interesting phenomena. You can code it. I coded it up on my computer. You can run simulations. And you will see the wealth. If you take the log wealth, it will look like something like this, like up, then boom. What happens here? Here you will get bankrupt. Okay. So you want to be a tiny bit before, and a tiny bit before. This is where you will maximize your wealth. It's probability 1. So fascinating number. This number happens to be the X star, exactly the X star that we're talking about here, when we talk logarithm of the wealth. And I can define it formally, and hopefully I will in this course. So I can model this rigorously and talk about what's my maximum wealth I can achieve. And the generalization of that is called, universal portfolios, I should have started with that. I see you're all paying very good attention to me now. Universal portfolios, and this is by Tom Cover in '89. So he talked about a generalization of the Kelly. I'm Jerry. I'm guessing you didn't hear about that. So that's a generalization of Kelly criterion to portfolios. When I was a student, I looked at Tom Cover's papers, and I was shocked that it's possible. He was a professor at that time. He passed away, a very famous information theorist and really a wonderful scientist. So he talked about how do you maximize your wealth in a general market, really lovely model. He created a hedge fund. His hedge fund failed, by the way. But some of the techniques I will talk about, and some are, you will see why it failed. There is a computational issue with his method, which you can resolve, actually. Some of the resolutions are actually successful. They are used in finance, to the best of my knowledge. And yeah, overall fascinating topic. So you're asking, you had a small question, but I gave you a very long answer, I guess. It does relate, this theory is rooted in some of these interesting information theory type. Kelly was an information theorist as well. So Ed Thorpe wrote a book about him. I urge you to read it. Something about gambling. So he has the history of gambling and betting. And the scientific aspect of it is in something called information theory. And that has a lot of roots to universal prediction, which later gave rise to online convex optimization. When I was a student, I read this Tom Cover paper, and the first papers, Zinkevich's paper on online gradient descent just came out, and somehow I continued studying a generalization of it, which I will maybe talk about next week. So good, that's it for today, and I'll see you next week. Rohit will be talking Thursday.